Today we are going to finish 8.8 part 2, power series, derivative and integration. So after we take the derivative or integral of a power series, what's the interval of convergence and the radius of convergence, and what's the relation between the derivatives and the original function. In order to find the derivative or integral of a power series, derivative or integral with respect to x using the respective power rules. So power rules, because the power series, when we take the derivative or antiderivative, we are going to use power rules. And for each derivative or antiderivative of a power series, the radius of convergence will stay the same. So r stay the same for all the derivatives and antiderivatives. However, the interval of convergence, will be different in the endpoints. The interval will be the same, but at the endpoints, it might be a little bit different. Let's have a look. So look at example 1. Find the radius of convergence and interval convergence for the original function f(x), integration, first derivative, and the second derivative. So original series, so our center, so f of x equals this. Center is 0. We take the limit ratio test, an plus 1 divided by an. Limit, we plug everything in, negative 1 plus 1. We flip the denominator and go to infinity, n plus 1 over n plus 2 times x to the first. As n go to infinity, this part, n plus 1 over n plus 2, will be equal to, so this will be absolute value of x. We set this less than 1, so this gives us r equals 1, and x is between negative 1 and 1. Now we have to check at x equals 1. We plug in negative 1 to the n, 1 to the n plus 1, which is 1. So this is negative 1 to the n over n plus 1, alternating series. So this one converges. And at x equals negative 1, we plug it in. Negative 1 to the 2n plus 1, because 2n plus 1 is always odd, so this will be negative 1 over n plus 1. Very similar to p series, so this one diverges. You don't have to show steps, just conclude it diverges. So the radius of convergence is 1, and interval of convergence, which will be negative 1 and 1 closed here. You have to include 1 here. So after we get radius of convergence, we don't have to do the radius of convergence and the limit the ratio test for all of them. So all the radius here equals 1. The only difference is right now we have to adjust the boundaries for interval convergence. For example, integration f of x dx, when we take the antiderivative power rule, so we are taking derivative, antiderivative of this. This gives us integration as sigma notation, negative 1 to the n, x to the n plus 2 divided by n plus 1 times n plus 2. The constant c, we don't have to worry. And now let's have a look at the interval convergence. So based on the theorem here, if you look at the side notes, so for fx, once we know the convergence or divergence of fx, once fx is closed, all the upper levels will be closed. So we don't have to deal with negative, deal with 1. So 1 will be closed. We just need to see at negative 1 should be open or not. So let's have a look at negative 1. Plug negative 1 in here. Sigma negative 1 n plus 2 over n plus 1 times n plus 2. So negative 1 to the 2n plus 2 is always even. So this will become sigma. Negative 1 will become 1. Even power will be always positive, n plus 1, n plus 2. You don't have to simplify it. This is very similar to P theory, P equals 2, so this one converges. So our final answer, interval convergence for this one will be closed interval negative 1 to positive 1. So once on each side for f of x, once it's closed, all the upper levels integration or double integral will converge. We don't have to prove it. However, if you look at f prime of x, when we take the derivative, so everybody look at the notation, n should start from 1. Every time we take a derivative, we just change it to 1. Power rule, so it's n plus 1 times x to the n over n plus 1, which is negative 1 to the n times x to the n. Because on the left side, negative 1, it's open interval. Once it's open, all the lower levels will be open. So negative 1 will be open. We just need to check at x equals 1. We plug x equals 1 in, so f prime equals negative 1 to the n times 1 to the n, which is alternate series, so this diverge. So for f prime, the interval of convergence will be negative 1 to 1, all open, and the radius will be 1. So because f prime is open, so for f double prime, when we take the derivative, we change the boundary from 1 to 2, n times x to the n minus 1. However, interval convergence, we don't need to do anything, will be negative 1 to 1. Radius of convergence stay the same, and interval convergence, once it's open, for both sides, for either side, if it's open, all the lower ones will be open. So once we get the interval convergence for f of x, once this is open, either side, all the derivatives, you don't have to show, it's all open. If it's closed on any side, all the upper ones will be closed. You just need to check the other one. Everybody can try the next problem yourself and compare your answers with mine. This is answer key for number 2.